Awesome. Thanks, Kevin. All right, everyone. Good evening, and want to welcome everyone to North Jersey Astronomical Group's February 2025 monthly meeting. We're going to open up today's meeting with a presentation by our very own Chris Mauro, titled "Exoplanets: Finding Strange New Worlds," and he's going to take us on a journey on discovering exoplanets and significant scientific challenges that are presented when they're observed, during observation and identifying, whether these are planets or just some other type of blips that that are out there in the solar system. So look forward to your presentation tonight, Chris. Following Chris's presentation, I will ask that all of the members stay online for the second portion of our event, which is the business meeting. Yes.
And everyone can hear me.
Yes.
Very good. Well, good evening, everyone, and thank you for coming to tonight's talk. Tonight, we're going to examine exoplanets and the discovery, the classification, and finding strange new worlds. You may recognize that I lifted that from the intro to Star Trek. So every week we finding strange new worlds. Okay. Go. So why do we bother to find exoplanets? It's certainly can give us a lot of information about our place in the cosmos, give us information about our assumptions regarding planetary formation, as well as the star formation. But more importantly, it's answering questions like, is life abundant in the universe? We only know of life present on one planet currently, and there's a quest to see where else life could exist. And then the bigger one would be intelligent life. And probably the last reason is because we can. The technology has improved to a point where, as Omar had referred, these are very precise measurements. Technology has improved where we have the capability to measure very, very small changes in a star's position or in Doppler. And we'll talk about those things. What's going on here? Okay.
Here's something that sounds like the Doppler effect.
Yeah. There we go. Okay. So this is a very difficult process of identifying an exoplanet. We have various measurements we can make, various inputs that we have, but all of them involve complex, specialized equipment. Spectrometers that are very detailed and precise and can measure the changes in the shift of the wavelength, identifying the location of particular stars can come down to a point where it's as little as 1 pixel. So these are very, very precise calculations. And it requires very accurate calibration and operation. And there were also numerous and very lengthy observations when you're looking at a transit. You're watching the planet go in front of the star. That can take a long time, and you have to constantly monitor the progress of that. So there were some difficulties. There's one example I wanted to kind of discuss with you. There was many people that have made accidentally made false claims of finding planets. This goes back to the mid 20th century. One of them was a Dutch astronomer working in the United States, Peter van de Kamp. And he had spent a lot of time observing and watching Barnard's star. He had taken over 2,000 photographs. And he was making astrometric measurements. And he published a report in the 60s indicating that he had found one planet, and then later in 69, he found another planet. Well, it wasn't too long before other astronomers refuted his claims and were able to demonstrate that he was inaccurate. The irony is that there is a planet orbiting Barnard's star, but when it was discovered, it didn't fit any of the camp's descriptions anyway. So what are the things that we can measure about a star and also measure about a potential exoplanet? Well, the first is spectroscopy. We can analyze the star's spectrum. So you receive the starlight, you put it through a prism or diffraction grating, and you create a spectrum of the star. And you will notice that you have absorption lines of where different elements are present or are absorbed by the star and not present in the starlight. And the second measurement is photometry. We can measure the luminance of the star and its changes. And the third and final is the astrometry, where we measure the star's position in space. And this is where we have a very precise measurement. So I'll give you an idea about how detailed it might be. Suppose we were on Alpha Centauri and we're looking back at us 4.2 light years away. What would we see in our sun resulting from Jupiter transiting in front of our sun? We would see our sun slowly oscillating back and forth over almost 12 years. Shift in its position would be approximately 3.7 milliarc seconds, which is a very tiny measurement. Hubble, in its fantastic images that we saw of deep space, each pixel measured 50 milliarc seconds. So it's easily an order of a magnitude more precise that we need to have. The Webb scope does have a very high resolution, pixel size. They can register down to 3.1 milliarc seconds. So they would be able to potentially identify Jupiter-sized planets. It still does not enable them to measure Earth-sized planets. It's still not that precise. So let's look at some of the methodologies. First is the transit. And this is an animation from NASA that shows a planet transiting in front of the star. And you'll notice on the lower left that the photometric data changes and the light has diminished. So again, if we were going to use Jupiter as an example, Jupiter blocks about 1% of the sun's light. If someone were looking from afar, looking at Jupiter transit in front of the sun, it blocks about 1% of the light. The Earth would block 1/100%. So it shows here again that it is very difficult to find Earth-sized planets. So let's look at some of the advantages and limitations of the transit method. We can measure the size of the planet. We can yield precise measurements. And there is a potential for atmospheric study as the planet transits across the star. Limitations, of course, are the orbital alignment with the Earth is required. In other words, the orbit needs to be perpendicular to our line of sight. Less effective for small planets. And the eclipsing binary can give false positives. And it does require continuous observation for a long period of time. The next measurement is the radial velocity, which is expressed through a Doppler signature, or and it shows up, or at least it's discussed as the wobble of the star as the planet revolves around it. As you notice, what the two objects are actually orbiting around the barycenter of mass between the two of them. And so what this shows is as the star comes toward us, the wavelength of light is compressed, and you have a blue effect to it. And as it moves away, you have a red. Oops, I don't want to do. So the radial velocity, it measures the orbital eccentricity and the estimate of the minimum mass. Those are some of the parameters we can derive. It also can estimate the planet's density together with other observations of the star. It does not need special alignment, and it's well suited to detect large planets. It's also used to confirm candidate planets. Limitations is it requires precise measurements as well as complex spectrographic equipment and long observation. You can also have false positives due to either stellar activity or other phenomena. So the surface of the star is not a flat surface. It's a round object, of course. And there are a number of factors that need to be corrected for. One of them is the undulations or activity on the surface of the star. As it moves, it changes that Doppler signature that you're going to look at. And the other thing is there is something called photon noise. These are, spurious photons that can land on your sensor and distort the measurements that you're making. The next methodology is called direct imaging. And this takes a direct photograph or a direct impression of the planet. But it does require, again, some specialized equipment. Okay, here we go. Oops, sorry. Okay, so this is an animation using a coronagraph to cover the star. And as you cover the star, the impression of the planet is revealed. Do that one more time. So let's look at some of the advantages and limitations. Certainly, observing the planet directly would confirm the candidate. It could also yield atmospheric data as we look at the reflection of the planet. And we can observe the orbit. We can see where it is in relation to the star. And it's less prone to false positives. Limitations, it is difficult for close planets. If you can imagine trying to find a firefly in the midst of a searchlight, if the firefly is 1 inch away, it would be very, very difficult to identify that planet. It does require precise and complex equipment, the coronagraph, and something called a star shade, which I had never heard of. This is an object that's obviously placed out in a distance from the telescope, and it essentially blocks the light from the star, but allows you to see outside of it. And it works best for large, bright planets. So what you see on the right are the two objects. One is the star shade, and the one on the bottom is the coronagraph covering the star, and you can see where the planet is now visible in the lower left. And the next methodology is gravitational microlensing, and this takes advantage of the fact that light waves are bent around objects that have mass and have, as a result, have gravity. So here's a star, and it gets eclipsed by a planet or another star, and you see the gravity well, and it bends the light waves. You would think that it would be difficult to make this work, but it's interesting that there's been quite a number of candidate exoplanets that have been discovered this way. What you look for is basically something called an Einstein ring, which shows the light that's bent around the object as it passes and as it eclipses and passes in front of the star. So the advantage is that it can reveal planets in distant star systems. It's suitable for observing large numbers of stars in the center of the galactic bulge. This is what the Gaia spacecraft was designed to do, and it works for planets not found by other methods. Limitations: it is a one-time observation. You can't go back and repeat it. So you have to wait till there's another planet on a different star to get the next observation. It does yield limited information, and it does require precise alignment of the planet, the star, and the Earth. The next method is astrometry. Basically, that plots the exact position of the star as the other stars and planets have influence and its location. So here you need very, very precise sensors to measure the actual position. The advantage is there's no alignment needed, the potential to detect wide orbit planets, and it can be used to measure the mass of the exoplanet. It does require precise measurement, and it's most effective for nearby stars and less sensitive for smaller planets. This is the least effective way of finding exoplanets. So if we look at the current total, and this is a relatively up-to-date NASA number, 5,760 exoplanets have been discovered. Transit method is by far the most successful, with over 4,000. The radial velocity Doppler shift, a little over 1,000. Microlensing, about 235. Direct imaging, 82. And astrometry, only 3. Just for people who are curious, you can calculate the mass and other variables based on Kepler's laws. And here are some of the formulas if anyone is interested. So now the search begins. So as I mentioned earlier, in the mid-20th century, there were no successful discoveries. But when they examined them, there were numerous false positives. We had to wait for the technology to catch up. So a couple of milestones. In 1938, Berlorsky proposed using a transit photometry data or an approach. In 1952, Otto Struve suggested using spectroscopic methods to find exoplanets. 1988, Latham observed what he thinks is a brown dwarf. Later, it would be proven to be an exoplanet, but that was a number of years afterwards. 1992 is the first major accomplishment. Wolfskin and Frail discovered the first exoplanet orbiting a pulsar. They were radio astronomers, so that's why they were looking at pulsars, and they were surprised to see that the radio waves emanating from the pulsar would vary and it would change. In 1995, Mayo and Kelez discovered the first exoplanet orbiting a main sequence star. And they would later receive a Nobel Prize in 2019. So the star and the planet, the star is 51 Pegasi, the planet is 51 Pegasi b, and you could see that it's a G-type star with a large Jupiter-sized, bigger than Jupiter-sized planet around it, and it's in a close orbit 4.2 days. So this is considered as a hot Jupiter because as it gets close to the star, it's roasting itself. So here are some comparisons. The planet comparison, 51 Pegasi b is 47% less, 50% larger than Jupiter, but 47% less massive, so it's much less dense. And comparing it to our sun, 51 Pegasi is 23% larger than our sun. So just a comment on confirmed versus a candidate. We currently have 5,800 or so confirmed planets, and there are 7,000 or over 7,000 candidates waiting to be confirmed. There are 4,359 different solar systems that we've identified with multiple planets. Now, a candidate is observed, but it's not yet proven to really exist. And we have to be aware that there are numerous false positives. The confirmation requires additional observations by 2 other telescopes. And as I mentioned, there's a large backlog of candidates waiting for confirmation. Just a quick note on naming of new stars and planets, because you'll see names like, Kepler 20e or KOI 961.01. So the first part is the telescope name or the survey name. For example, Kepler or HD for Henry. I can't read that because I got people in the way. All right, followed by a number, which is the order in which the star was cataloged, followed by a lowercase letter in the order of, which is the order of discovery. And there are some exceptions. But the first planet that's discovered around the star is given a lowercase b, followed by C, D, and E, and so on. So, for example, you have Kepler 16b, or the Earth would be Sun D. And in multiple star systems like Proxima, the uppercase letters designate stars and lowercase letters designate planets. You may ask why they start with B, because in a multiple binary or trinary star system, the star is given the letter A, a capital letter A. So let's look at some of the instruments that we've had operating over the past number of years. So the first one I would like to show you is the terrestrial telescope. This is a European Space Agency, HARPS, which stands for High Accuracy Radial Velocity Planet Searcher. It has a 3.6 meter mirror, which is a little more than 11 feet. And the key thing about this installation is that the spectrometer is in an isolated, separate room. And as you can see, it's on rails and it's bolted to the floor so that it doesn't move. The reason for that being that any slight movement is going to distort or give false readings on the spectrograph or the spectrum. So, so one of the techniques in the spectrometry is to use a gas like iodine gas, where you have known absorption lines, and then you can compare your images and see where the shift is. So if the gas absorption lines don't move, and yet the spectrum from the star moves, you know that that's a shift. Otherwise, they both would be moving in the same direction. So I think everyone's familiar with Kepler. Kepler was quite active from 2009 to 2018. It had its extended mission was called K2. It is in a heliocentric orbit, so it's essentially orbiting around the sun. It does have a narrow but yet deep field. So some of its discoveries go out to 1,000 light years and even some further than that. And it's credited with discovering some 3,000 plus confirmed planets and almost 3,000 candidates. It is not currently active. It has run out of fuel to maneuver and point itself where the scientists would like to go. Another very successful exoplanet finder was Gaia, which is part of the European Space Agency. This one has a wide field, and so it has a little different result than we got from Kepler. And it is in a Lagrange point, the Sun-Earth L2. Its mission is to survey the entire sky. And it's measuring both the astrometric and photometric data. The primary goal is to create a 3D image of space. So, and along with that, it has discovered a number of exoplanets. And currently it is low on fuel, so it's due to wind down this year. We also have TESS, the Transiting Exoplanet Survey satellite, which is still active. It's in an extended mission. It's in a highly elliptical geocentric orbit. Its field is also wide, 400 times larger than Kepler. And basically it's designed to identify using a transit method. Currently discovering over 500 confirmed planets and 7,000 candidates. The European Space Agency also has CHEOPS, the Characterizing Exoplanet Satellite. This is one of the low budget programs that the European Space Agency has. They break them down by small, medium, and large. So this is in a not necessarily a low Earth orbit, but it is in an orbit about 400 miles above the surface of the Earth. It's polar aligned, and it's sun synchronous. And it's designed to do some follow-up observations, get more accurate data on the mass and radius of existing candidates. And then, of course, the James Webb Space Telescope, launched in 2022. It also is currently in a Sun-Earth L2 halo orbit. It has a wide and deep field of view. It's designed primarily for infrared astronomy, and it is directed toward exoplanets. It has a near infrared spectrograph, which will provide some interesting information. So if we look at our solar system as a model for what we would like to look for outside, we notice that on the inner orbits are the small rocky planets, followed by the large gaseous and ice giants. The solar system has a habitable zone, which is a zone where water is below the snow line. So it's in the form of liquid water, not frozen, and it's liquid and it's not boiling away. So on the inner part would be too warm, the outer part would be too cold. What makes our solar system particularly unique is the stability of the stars and planets. Our planets are well behaved. They're in stable orbits. Our star is also pretty well behaved. We're not bombarded with radiation of very high magnitude. So we're in a Goldilocks zone. So another interesting observation about our solar system is that the inclination of the orbits are very close to the inclination of the Earth's orbit. With the exception of Mercury, the largest variation is that of Saturn at almost 2.5 degrees. The orbits are relatively circular. The eccentricity is also quite low, again, except for Mercury. The Earth, for example, is a 0.017 eccentricity. So what have we cataloged at this point? Well, we have a gallery of planets, all different the sizes, different makeups, different content. We have some planets that are as small as twice the mass of the moon. We've discovered some as large as 30 times the mass of Jupiter. Some are orbiting binary stars. Some are orbiting pulsars. And we have seen a variety of solar system structures. We've got large giant planets in close orbits. We've seen hot Jupiters. We've seen Hycean worlds. These are planets that have hydrogen atmospheres and a water surface. We've identified lava worlds, and we've identified the super Earths and mini-Neptunes are the most numerous of the exoplanets that we've discovered. We've also noted that type M stars are the most numerous star type. And we'll go over the demographics in a minute. So here's the observations. So there are four basic types that we categorize, starting with the gas giants, which are Saturn or Jupiter sized. Next would be Neptune sized. And these would have hydrogen and or helium. Then there's a super Earth size, which is a terrestrial planet, but it's more massive than the Earth, but lighter than Neptune. And lastly, a terrestrial size, which is similar to our Earth and smaller. So here is a graph of the planet demographics and something called a Fulton Gap or a radius valley. So you see on the left side of the graph, you have example of Mars and the Earth, followed by a group of super Earths, then the valley area, then sub-Neptunes, and then Neptune. So the blue bars are actually observed, and the red bars are results of simulations. So the simulation matches the observations reasonably well. And there's no explanation, at least that there's some theories, but no concrete explanation as to what has caused this valley. This classification of main sequence stars by color, O through M. And what's interesting about this slide is you can see the absorption spectrum, absorption lines in the spectrum on the left side. And here's the star demographics. The large OA and B type stars, well, less than 1%. The F type, about 3%. G type, which is like our sun, 7.6%. K and M round out the remainder. Interesting thing about the M type, they have the longest longevity, 100 billion years. And yet the X-ray radiation in the habitable zone is 400 times larger than what the Earth receives from our G type star. And 3/4 of the stars out in the Milky Way are M type. So a couple of interesting exoplanets. There's the K2-18b, which is the Hycean planet with the liquid water surrounded by a hydrogen atmosphere. Kepler-16 is a circumbinary. Planet is a Saturn-sized planet. TRAPPIST-1 has 7 planets, 40 light years away from us. 3 of them, the D, B, and F, have water. E has a magnetic field, and the star is relatively quiet. So that's one of particular interest. There's another planet called a dark night, which is a star that is a planet that orbits around the pulsar, around the neutron star. And it is contents is carbon. And the theory is that under high pressure, that the interior of this planet would be a diamond. So it's called a dark night because it's not reflective at all. There's something called Tabby's star, which has variation in its luminosity that is difficult to explain. one theory is that it may have a Dyson sphere surrounding the star, which would indicate a very, very advanced civilization. And the list goes on with a couple more. There's Kepler 11, which has 6 planets, Kepler 12, Kepler 20, which has 5. And KOI is a Kepler object of interest. So KOI 5AB, the planet orbits a triple star in Cygnus. So here's an artist's impression of what it might be like, with the double star. And here is some suggestions of what the content or construction of the TRAPPIST exoplanets might be. So what about the next generation? Getting close to time. So we have a couple of terrestrial telescopes in the works, and we have some orbiting platforms in the works. So the first one is the European Southern Observatory at the Atacama Desert. Is the construction of the extremely large telescope, the ETL, which is planned to be operational or have its first light in 2028. And this is a photograph of it. Just to give you a perspective, there's a car parked in the front of the building, and that shows you how big this scope is. Another project is the Magellan project, also a European Space Agency. It's planned for the 2030s, and it will also be in the Atacama Desert. So it has a 25 meter mirror, 83, which is 83 feet. It also has a feature of adaptive focusing, similar to I think the Webb telescope has that, where it focuses the individual mirrors. In the fall of this year, we should be launching Pandora. Pandora is a small satellite mission. It's a low budget mission, and it's basically equipped to identify planets with hydrogen or water in their atmosphere. It will observe 20 stars and 39 planets, planets from Earth size to Jupiter size, and host stars from mid-K level to lower surface temperature M or late M. So this is just an example of photometric data from Pandora. European Space Agency also is launching Plato 2026. And that stands for Planetary Transit and Oscillations of Stars. This is a medium class mission for ESA. And it will be in the Sun-Earth L2 Lagrange point. It's getting very crowded there. We got a lot of orbiting satellites there. And its primary directive is to seek Earth-like planets orbiting Sun-like stars of G or K, and identify planets in the habitable zone. Secondary objective is to study the stellar oscillations or seismic activity in stars. Another mission or project is the Nancy Grace Roman Telescope. Nancy Grace Roman was former NASA chief of astronomy. this telescope will also be at L2. It has a 2.4 meter mirror with a chronograph and spectrometer, visible and near infrared. This was a gift from the National Reconnaissance Office, which I believe is part of the Department of Defense. So this was one of the Defense Department's, gifts to us, that came off their books, and it was sitting out in space, and so we're going to use it. Lastly, ESA has for 2029, Ariel, the Atmospheric Remote Sensing and Infrared Exoplanet Large Survey, and targeting 100 known exoplanets. Chart the demographics. It's going to utilize a transit spectrograph, and it also is going to be at L2. Coming soon. Where are they? The search for life. That'll be the next topic. Thank you. Thank you for paying your taxes.
Thank you very much, Chris. That was definitely a lot of information provided there. I certainly appreciate it. So gonna go on ahead and open this up for questions. So if anyone has any questions for Chris.
Thank you, Ed.
Okay,
Thank you,
well,
Chris.
thank you. Well, I do, Chris. You spoke about the habitable zone. And you always hear, some articles that I read on some news sites that, they, found a possible candidate. I mean, have any of these exoplanets that have been discovered or potential, been possibly classified as, falling within that category?
Yeah, there are a few, very few, between 10 and 20.
Really? Okay.
Earth-like planets that are in the habitable zone of their star. Now, the thing about the stars, that, like I mentioned, the M stars are most numerous. M stars are unstable. They put out a lot of radiation. Also, as you have a smaller star with less temperature, your habitable zone moves closer to the star itself. And what happens there is you end up running the risk of being tidally locked because you're so close. And that would not be good for developing life. Although there's some theories that say you could develop it around the terminator, because you're sort of halfway between the dark side and the light side, but that would be very niche life forms if that was the case.
Okay.
So yes, there are some potential candidates that need to be further explored. I think with the new telescopes that are going up, the sensors that they have are much more, like an order of magnitude, in some cases 2 orders of magnitude more sensitive than the ones we have now.
Interesting. All right. Yeah, thank you. Appreciate that. Anyone else have any questions? No. All right. Thank you again, Chris.
Wait, I have a quick question.
Oh,
I
yeah,
just
go ahead,
couldn't
Mark.
unmute fast enough. Mark
No
Siegel.
worries.
So obviously we're just looking at the Milky Way, and we probably can't look very far in the Milky Way, but how many of the stars that we can see do they think that they've looked for a planet on, and how many are we missing? How many stars are we missing?
That's a good question. I don't know. I don't know what the population of that they've explored.
Yeah, I'm not sure either, but it's a very small amount, because like Kepler and some of those other spacecraft have only looked at stars in the local neighborhood, you know.
Hmm.
And so it's a pretty small, it's quite a large number that they've surveyed, but it's pretty small compared to the 200 billion total stars that are in the Milky Way, you know.
I think, Mary Lou, I think you wanted to add to that.
Yeah, I wanted to say that even though we haven't looked at many stars, although you keep saying there's 7,000 possible ones here and 7,000 possible ones there, we have looked like quite a number. But the thing that excites me is of the stars we have looked at, about half of them have a planet.
Right, right.
So the percentage of planets is pretty big.
Mhm.
Yeah.
And some of them are doubles or triples, so it's almost onesies for the number of stars that have planets.
Yeah, no, that's exciting. Yes, yeah, it's an area of research that I'm not familiar with. So, when I hear about these things, yeah, I didn't realize it was almost a 1-to-1.
Mhm.
That's awesome. And one day
That's
we'll,
the current estimate.
gotcha.
It might even be more.
Mary Lou may know the answer to this, or maybe you do too, Chris. Is the Kelp project still in progress, or did that stop?
That pretty much stopped.
Okay.
And people moved over to be follow-up people for the TESS group. But they have
Gotcha.
really strong requirements, so the AAI telescope was not quite good enough for that.
Okay.
But it was fun when we were part of the Kelp project.
Yeah.
Yeah.
That was over 10 years ago, I think now about.
Yeah.
Yes, so we need citizen astronomers to
Mhm.
help with this backlog.
Right.
I got a
Awesome.
question.
Yes.
Go ahead.
Chris, are they strictly looking in our own galaxy? We're not looking outside there yet, or we don't have the ability to get that kind of resolution yet, right?
No, but we're
Yeah.
only in our galaxy.
Just the local stuff.
Yeah.
Okay.
Local to a point. Remember, Kepler has looked out as far as maybe 1,000 light years, maybe 2,000. Not much whole lot further than that. TESS is only very close. So we've just scratched the surface. And
Yeah.
also, when you're looking at transits, because of the requirement that the orbital plane be perpendicular to our line of sight, eliminates a lot of other intersections. So if we moved to a different location, we'd see other transits. So
Okay. Well, again, thank you, Chris. Any other questions? No? All right. So we are going to go on ahead and move into the second portion of our meeting today, which is the business meeting. So we asked all of our attendees to please stay with us.